Here's another example of how you would use the Lenz's law to find the direction of the current in a loop. Let's say we have a magnet here. Here's a magnet, and let's say that, let's give it north and a south pole. So let's say that, let's still use the north on a closer side, and here's the south. And so that would give us a magnetic field that points like this, right? So here's the magnetic field produced by this magnet, and maybe I'll put one more right in the middle. And of course, these lines extend; they continue on. I just drew them. That's all I drew there. And then on this side, I should also have the magnetic field that points towards the south pole. So something like this is what I should have there. And then maybe I'll add a loop here and another loop here. It should look a little better than what I drew. But anyways, there's that. So here's your magnet. So let's say that, not that it really matters, but let's say that it's the magnet that moves at velocity v towards the loop. So this is what we have. And if that's the case, then there's a changing flux through the loop, and that implies there's going to be a current in the loop. And the question is, in what direction does it flow? Let's use the Lenz's law. Now remember that Lenz's law says that the current in a loop I will always act in a way as to oppose the change in flux, oppose change in magnetic flux. So what we have at the loop is that if this magnet is moving to the right, then the magnetic field, the blue magnetic field, points through the loop. So I'm going to draw it pointing through the loop. And this blue magnetic field is increasing to the right. Now that means that there's going to be a current in a loop set up in such a way as to give us an opposing magnetic field. So if blue is increasing to the right, then the magnetic field of the loop is going to have to increase towards the left. And that can happen only if, let's see, which way should the current flow? So the current is going to have to flow like this. Current is going to have to flow in this direction. This is going to be the direction of the current I, and on the other side it's going to have to come back like this. This is the direction of the current I, and I know that that's the case because by using right-hand rule, the other right-hand rule, what I would do is I would take the thumb of my right hand, point in a direction of this arrow, and then curl my fingers. When I do that, I would see that the magnetic field would have to come out of this. I draw this, I guess I can draw it like this. It would have to go like this all the way around and then point into the page there, so it's coming out of the loop on this side. Now, if I were to draw it here, I would draw it maybe on the top. I will draw it like this. This is how this magnetic field has to point. So it points like that, and that implies that the green field is just going to point in this direction. And so it will oppose the increasing blue field. And it's not the most glorious drawing I've done, but hopefully you can read it. So there it is. There's your direction of the current I. Now suppose we do the same example, but we flip the direction of the velocity here. So this is going to be so that the magnet is moving to the right instead of, I'm sorry, to the left instead of to the right. So let's say that we make this magnet now move away from the loop. Well, things will change. We will still have the changing flux is going to be present in through this loop, since in this case what will happen is you will have a magnetic field that points, the blue magnetic field that points through the loop. I'm going to draw that. The blue magnetic field still points through the loop, to the right, but because the magnet is moving away, because the magnet here is moving away from the loop, this magnetic field through the loop is decreasing, getting weaker, right? If you take this magnet and you move it away from the loop, then the magnetic field through the loop is getting weaker. Now remember that using Lenz's law, the current in the loop is going to be in such a direction as to oppose the change. Now, if you want to oppose the change, then you have to set up a magnetic field that points to the right as well, and it's increasing, so that you supplement for the loss. So the current here will flow in such a direction as to set up the magnetic field pointing to the right and increasing. So the magnetic field B here is going to be increasing. That green field is the field set up by the current, and so the current would have to flow. Which way would it have to flow? In order for that to work, the current would have to flow in this direction. This is I, and along the other side it would flow up like this. There's your I. So you would take your right hand and you would point the thumb in the direction of this current I, and then curl your fingers, and you would see that the magnetic field would have to point into the page here and into the page here. All right, so think about this one here. If the magnet is moving away, then the blue magnetic field, which is pointing to the right, is getting weaker and weaker and weaker. That means that the current is going to, in order for the current to oppose the change, it's going to have to set up a field pointing in the same direction that is increasing to supplement for the loss. And that can happen only if the current flows in the direction indicated. Okay, and then let's maybe do one more example. Here's another example. So let's say that this magnet, well, first let's draw the magnetic field of this magnet. So the magnetic field here would point like this, and like this, and like this, and of course it would continue so that it would point through the loop as well in this direction. And let's just add for completeness something on this side so that the magnetic field points towards the South Pole, and then I'll do a loop here, and I'll do a loop here, and let's say that that does it for the magnetic field of this magnet. So let's say that this magnetic field, let's say that this magnet is moving away from the loop, so that the velocity of this magnet is in this direction. This is the velocity of the magnet. Well, whether the magnet moves to the right or to the left, the magnetic field through the loop always points to the left, because this is where you have the North Pole. So the blue field through the loop will always point in this direction. But because the magnet is moving away, the blue field is decreasing. All right, so now that we know that the blue field through the loop is decreasing here, we can tell that the loop itself is going to set up its own magnetic field that will supplement for the loss, because the loop will, by Lenz's law, the loop will oppose the change, and therefore it's going to set up its own field that points in this direction, and it will be increasing to supplement for the loss. And that can happen only if the current flows, let's see, in this direction. So the current has to flow like this. And I'll draw it on the top there. The current has to flow like this. So let's make sure that that does work out. So take the right hand, take the thumb of your right hand, make it point in the direction of the arrow, curl your fingers, and then you will see that if you do curl your fingers, the magnetic field will in fact point into the loop here and out of the loop in this direction. And on the top, if you do set up the thumb of your right hand to point in the direction of this current, and then curl your fingers, the magnetic field will point into the loop, through the loop, and it will come out like that. And so what that gives me is the green field that points through the loop to the left, and it must be increasing. All right, so there's that. And then maybe one more. So I'll do one more example. So here's this case where you have the magnetic field, but now the North Pole is on the right hand side. Let's draw the field in this case. I'm going to have the magnetic field that points towards the South Pole. And okay, on the right hand side it points away from the North Pole. So I get something like this. I'm going to add a loop here. There's a north, as a north to south. And I have enough room to add another line. Okay, and so the magnetic field through the loop, in this specific case, is going to point to the right. So here's the blue field. The blue field points to the right. And now let's see, let's determine whether we want this magnet to move away or move towards the loop. Let's see which one would be more confusing. Let's just say that it moves in this direction. So here's, let's say that it moves at the velocity v and moves away from the loop. And so using the Lenz's law, the current in a loop would be set up in such a way as to oppose the change. So what's happening here is the magnetic field points to the right, but that magnetic field is decreasing, right? It's a decreasing magnetic field. Decreasing because the magnet is moving away. So that implies that the loop itself is going to set up a magnetic field that opposes the change, and so it supplements for the loss. And so the green field set up by the loop would have to point to the right, and that green field would have to be increasing while the other one is decreasing. This way you oppose the change. And so the only way this could happen is if the current flow in, let's see, which way do we need it to flow? If, yeah, there we go. So you'd want the current to flow like this. Here's I, and then through the bottom, you would want the current to flow like that. Here's I, and let's make sure that this does work out. So use the right hand, take the thumb of your right hand, point in the direction of this current I, curl your fingers, and you would see that magnetic field would have to point into the loop, then out the loop this way. Down the bottom, magnetic field will have to point into the loop and out the loop the other end. And so the loop, that the green field points into the loop, and it would have to be increasing to oppose the change. So there's that. There's your Lenz's law. You can use the Lenz's law to figure out the direction of the current in a loop when the flux through the loop is changing.